The contents of the lab report are meant for educational purposes only. They are not meant to be misconstrued as medical diagnosis or treatment advice.
Today, on the lab report, we're going to talk about catecholamines.
Listen up, all you adrenaline junkies.
Or the people with burnout.
The world of medicine can be challenging. Clinicians and patients are always looking for more options, more effective treatments, and in the end, more answers. Functional and integrative medicine focuses on addressing root causes of disease. Here at Genova Diagnostics, we've watched this field evolve and grow for over 35 years. We've not only adapted, we've led. Join us as we talk about functional medicine, laboratory testing, and optimizing health. Welcome to the Lab Report.
You like the window seat or the aisle seat?
Well, I like the window seat, but I keep the window closed so I don't look out because I'm afraid
You're
of heights.
one of those. That
I
is
am.
terrible. Hello.
Hey, Michael Chapman, how are you?
I can't believe that's what you do. Like, the whole row is trying to see what's going on outside. What's the weather? Are we in clouds?
That's right.
What's the landscape look like? And you're like lording over the window and
I keep it closed.
exerting your power by saying,
I
you
keep it
guys
closed.
don't get to see any of this.
I just don't want to see it, and I don't want to be on the aisle.
Duly noted if we go to a conference together. Anyway, this is a podcast called The Lab Report, brought to you by Genova Diagnostics, where we talk about things like functional medicine, specialty lab testing, and integrative therapeutics. And, it's a good time.
Yeah, we're so thankful that you're here, and if you're new, welcome. And if you're returning, thank you. And by now, we hope you would have gone to iTunes or Spotify, maybe subscribe to the show, left us some stars, rate, review, share with your friends, things like that.
If you have additional feedback, you can send that feedback to podcast@gdx.net. We haven't set up that voicemail yet.
Nope.
But we'll see. We'll see if we can get that going.
We could just give your personal phone number. We can call you and leave you messages.
Pass.
What are you on about?
Well, you said earlier we're going to talk about catecholamines today, which are neurotransmitters. Let's remind us, what is a neurotransmitter?
Well, when I think of a neurotransmitter, I think of the terminal button.
What?
Yeah. It's part of a neuron, right?
Okay.
And so it's where these little chemicals are produced and stored. Mm-hmm. And then when you get the explosion of signal from the rest of the neuron, it releases these vesicles that contain a bunch of these little chemical messengers into the synapse.
Wow.
And then the
then what
synapse allows these little chemical messengers to go to the postsynaptic neuron, where it acts on the, I believe, dendrites.
Wow.
No, that's
Go
not
ahead.
right. Maybe that's not right.
Keep going.
It acts on the postsynaptic neuron and tells it to lower its threshold of potential so that it will continue to fire. So they're like little dominoes, in effect. They allow for the connection between neurons. They send messages across them.
All right. Great definition, Michael. Thanks for that. Now, when I think about neurotransmitters, I think the one that most people think about is serotonin and, tryptophan. We've talked a little bit about this, but
Serotonin has a good PR agent.
It does. But then there's this subclass of neurotransmitters that we're talking about today called the catecholamines. So why do they have their own subsegment? What does that mean?
Well, they're defined kind of by their chemical structure. So they have a catechol group and they have an amine group. So that's where the name comes from.
Not very clever.
And the three catecholamines that really get the most attention are dopamine, epinephrine, and norepinephrine, or as they're more commonly referred to as adrenaline and noradrenaline.
I like those names because you think adrenaline, some of these are made in the adrenal gland, right? Adrenaline, adrenal gland. Noradrenaline, or norepinephrine, near the adrenal gland. That's really interesting. And then you also think, okay, epinephrine. Epi is above the kidney, and that's where the adrenal gland lives. So it's really interesting naming convention. But we're going to single out these three: epinephrine, norepinephrine, and dopamine.
Well, I think the first way to separate them out is to really separate dopamine from epinephrine and norepinephrine, because they're two totally different things, honestly. Dopamine is pretty much primarily acting in the central nervous system, whereas epinephrine, norepinephrine are acting in the periphery. They're epinephrine and norepinephrine, as you just alluded to, they're made in the periphery, whereas dopamine's made in the central nervous system. So very, very different molecules have very different actions, right?
Mm-hmm. But I think also importantly is we think, okay, we know that oftentimes amino acids are precursors to neurotransmitters, right? So if we're thinking about dopamine, norepinephrine, or epinephrine, what's the amino acid that you think about that is the precursors?
Tyrosine.
Tyrosine could also come from phenylalanine, so probably both.
And the thing I think, and biochemically, that's important when we're talking about phenylalanine and tyrosine and the conversions into dopamine, because that's kind of the first step there. I mean, there's L-DOPA, that's part of it and everything, but like the big thing we're going for is dopamine. Biopterin is a really important cofactor in those conversions, right? And iron is important as well. And so those cofactors must be present, and they're somewhat rate limiting.
So then you think about mood disorders, right? We think about neurotransmitters and mood disorders and how important nutrition is. Things like amino acids and iron and other cofactors.
Well, I guess, speaking of PR agents, if we're going down a ranking of who's popular, serotonin's number one, but epinephrine, norepinephrine might be 2 and 3 on that list.
Okay.
And that just leaves, there's other neurotransmitters out there, don't get me wrong, but B-list neurotransmitters, I should say, right?
Okay.
But we should be spending some time talking about dopamine because it's super important. And kind of word association, what's the first thing you think of when you hear the word dopamine?
Maybe like happy or the pleasure neurotransmitter.
Yeah, I think about chocolate.
Okay.
And I'm not even a
because
big
it
fan
makes
of
you
chocolate,
happy?
but
It's a reward?
Yeah, exactly. Because dopamine, it's kind of a reward system. And so we get these little dopamine hits when we get the things that we like, when we're pleasured by something.
Like when I do the dishes in the sink down here in our office.
It
makes me
You're
happy.
getting your dopamine
That's
fix
right.
by doing that.
I don't like dishes in the sink.
And I'll say this, even though we tend to think about dopamine as being kind of that reward system neurotransmitter, that's really limiting what it does because it does a ton of different things. It's involved in higher level executive functions, motor control, motivation, arousal, even things like nausea and even lactation. Like it's got a ton of different roles.
Well, it has roles even outside of the brain, right?
Yeah.
It has roles in the immune system. It can be synthesized and actually even be released by some immune cells themselves. And it actually works in other things like in the pancreas, in the kidneys. So there's systemic effects of dopamine, not only just in the brain.
Yeah, so dopamine, it's a big deal, right? You don't have adequate dopamine. It's associated with things like Parkinson's disease, where there's problems with the substantia nigra where it's being produced. So that's just a classic example of telling you how important dopamine is in executive function. Have you seen the movie The Awakening?
Oh,
The
with Robin Williams?
Awakenings.
Yeah, Robin Williams?
Yeah.
Yeah.
Yeah, it's a fantastic book too. I'd highly recommend it.
And I think Parkinson's disease is the perfect place to just realize how important dopamine is, because without dopamine, not only do you have the executive function problem like you just outlined, Michael, but other things like movement.
Saying about my executive function.
I'm just saying, when you see a Parkinson's patient, they have movement disorders where they get stiff and they're very slow and their limbs tremble when they're not in use. So without dopamine, you see the decline and you see why dopamine is so important.
And not only is dopamine important as the fact that it has its own actions, but then dopamine is the substrate for epinephrine and norepinephrine, right? And so it's tremendously important from that perspective as well.
Okay, so if we think of the pathway, right, we had phenylalanine and tyrosine making dopamine. So now we talked all about dopamine. Dopamine can be converted then, like you just said, to these other catecholamines. There's an enzyme called dopamine beta hydroxylase, which uses vitamin C and copper and then becomes norepinephrine. And then norepinephrine gets methylated to become epinephrine. So dopamine's kind of the linchpin right in the middle.
So yeah, maybe we should talk a little bit about epinephrine, norepinephrine, and what the importance of these are physiologically. Like, we can do the same word association game. What's the thing you think of when you think of epinephrine, norepinephrine?
Fight or flight,
That's what I was going to say.
because we share a brain.
So we hear a lot about this fight or flight. Maybe we should just briefly talk about what this is for people who maybe don't understand the full mechanism of it. What triggers fight or flight?
Stress, whether it's real or perceived. If you can have a stress response just sitting on your bed thinking about things, or you could be chased by a tiger. Something's causing you stress.
Yeah, and I tend to think there's a little bit of a distinction there between like acute and chronic stress, right? And we talked in previous episodes about the HPA axis, the hypothalamic pituitary adrenal axis. This is a different branch of the stress response, which is completely the autonomic sympathetic response. And so this is working through like your sympathetic neurons and all that immediate sort of thing where the HPA axis takes a while. So yeah, acute stress, but like really serious acute stress, like things are bad.
Yeah, like your heart rate goes up, you have palpitations, you're flushed, you're sweating. All of these stimulatory effects to try to get you to run is kind of what the catecholamines are responsible for.
Hence the name fight or flight. It's trying to get you to prepare for this emergency situation. And we've added in there freeze too, because they realize there's people like me out there in the world. So let me ask you this. This is something I've always wondered, right?
Okay.
So both adrenaline and noradrenaline, or epinephrine, norepinephrine, they're used in the sympathetic fight or flight response.
Okay.
And they cause a lot of this similar action. They're both beta and alpha adrenergic. So what is the difference physiologically between them? Like, I don't understand. Why have two neurotransmitters that are so similar?
They are very similar. But if you really parse it out and be very specific about it, if you think about epinephrine, its effects are more evident in the heart. So, your heart rate. If you think about norepinephrine, it's more in the blood vessels or your blood pressure. It's kind of like because I worked in the hospital for a very long time, in the middle of a code, we would give epinephrine to restart someone's heart. But then once you just wanted to keep their blood pressure up after you brought them back from the dead, you would use norepinephrine drips. So that works more peripherally on blood vessels.
So with that, we've got the fight or flight response where we have this excessive production of our epinephrine or norepinephrine, and then stress ends,
Right.
we escape,
Hopefully.
and the epinephrine, norepinephrine are broken down. We use two main enzymes to do that, COMT and MAO.
Catechol-O-methyltransferase.
Monoamine oxidase.
Yeah.
And when you think of COMT, here we are, another enzyme that requires a methylation step, that requires S-adenosyl methionine, or SAM, as the cofactor to complete that methylation. And so you may have heard of COMT. We did a podcast episode on COMT, right? And so what do we think about with COMT? Because we do a lot of genetics on this one. This is very common in functional medicine where we're looking at the genetics around COMT. And this is one of the main things we think of, how epinephrine and norepinephrine are being degraded.
So it makes perfect sense then. If you go back and listen to the multi-omics episode we did about COMT, we talked about how you need COMT to break down and degrade these catecholamines. So if you have a SNP, or a single nucleotide polymorphism, in COMT, or you have a methylation problem, these catecholamines stick around a long time, and these patients have a propensity to be a bit anxious, which makes sense.
And I would make this distinction because when we're talking about different patient populations, it's important to know that the most common genetic orientation for COMT is actually what's called heterozygous, meaning with one SNP and then one wild type. So actually, the way we designate it is a plus and a minus, just one SNP. So what actually is important is there's some literature to suggest, and people will talk on the podium about how actually having no SNPs in COMT might also be detrimental to certain patient populations because they're not used to that. And you can actually end up with too rapid of a breakdown of epinephrine and norepinephrine. So you notice I just mentioned the word breakdown of the catecholamines of epinephrine, norepinephrine. Is there anything that we can look at on a testing perspective that might be an indicator of breakdown of epinephrine, norepinephrine?
Well, remember, we did a whole episode on organic acids, and part of the organic acid section of the NutrIval metabolomics and the organic acids profile is a section that we call neurotransmitter metabolites, where we're measuring urinary excretion of some of the breakdown products of these catecholamines.
Yeah, so if we're thinking about specifically adrenaline, noradrenaline, or epinephrine, norepinephrine, right? Do I have to say that every time?
You don't.
Okay,
I think
I'll stick with epinephrine, norepinephrine.
Good.
So those break down into two main things, vinyl mandelic acid, and then another product called 3-methoxy-4-hydroxyphenylglycol. And those are direct breakdown products of epinephrine, norepinephrine. And so when those are elevated, that's something I do wonder about sometimes when somebody has excessive breakdown of epinephrine, norepinephrine, maybe such as when they're either producing a lot of it or if they're on a medication like an SNRI.
Right. And I think an important distinction here is that when we're measuring these things in the urine, right, people often take this and extrapolate back to say, is this the level of norepinephrine and epinephrine in their brain or in their systemic system. Not always the case, because these are then further metabolized down, and we're measuring them because we know they require specific vitamin and mineral cofactors to be further broken down. So elevations could also speak to nutritional deficiencies as well.
Can speak to nutritional deficiencies. I would say with respect to the epinephrine and norepinephrine, because those are systemically acting neurotransmitters, unlike dopamine, which is primarily centrally acting, then those two metabolites might actually be a little bit more of a tighter correlate to that systemic production. And research has shown that there is correlation between overall stress response and the level of these urinary metabolites.
Okay, so we just gave you the downstream metabolites of both epinephrine and norepinephrine, but then we forgot about dopamine, because dopamine also has a downstream metabolite.
And we made that whole big
I
deal
know.
about dopamine not getting its day, and here we are doing it to it. I mean, it's just not fair.
Well,
Why are we doing this to dopamine?
Well,
we need to eat our chocolate.
let's go back and let's give the downstream urinary metabolite of dopamine.
Homovanillic acid.
That's it?
That's right.
You got nothing else on it?
It's abbreviated to HVA.
Oh, good. Okay, well, I guess I'll take this one then. Dopamine, we know, breaks down to norepinephrine, and it requires vitamin C and copper, which we said earlier. So you might think in your mind, well, if someone has got an insufficient amount of vitamin C or copper in their diet, that conversion might not happen well, and dopamine might be higher, which would then lead to higher breakdown products like HVA, as you say.
Yeah, and another interesting thing about this pathway is that dopamine turns into homovanillic acid, HVA, through MAO and COMT enzymes. And so another theoretical possibility is that if you have a COMT SNP or if you have methylation issues, then that might slow the conversion, maybe even leading to lower levels of homovanillic acid. Oh my.
Travis,
there's other people that work in this building. We've already gotten complaints.
you know what time it is?
It's the question of the day. It's the question of the day.
Okay, so would you like to hear the question of the day, Michael
I
Chapman?
would. Yeah, lay it on me.
Well, it's really apropos because you're sitting over there drinking your big Dr. Seuss mug full of coffee.
As I do.
And the question is, how does caffeine or caffeine intake affect our catecholamines?
Yeah, this is an interesting one, not only as how it affects catecholamines, but just the stress response in general. Sometimes we've talked about cortisol and how caffeine can affect cortisol, and that it can, in the short term, raise cortisol levels, but then maybe that's attenuated as the body becomes more conditioned, I should say, to having multiple cups of coffee in the morning. But as it relates to the catecholamines, caffeine does seem to increase catecholamines in general, especially epinephrine and norepinephrine. I should be specific about that. There's one study where they actually looked at the effects of mental workload and caffeine on catecholamines, and what they found was that as the dose of coffee was increased, they noticed increase in urinary levels of adrenaline, noradrenaline, and their metabolites.
Wow.
So that was pretty interesting, and it also seemed to relate to mental workload increasing catecholamines as well. So
Okay, so keep drinking your coffee, but we left one out.
Okay.
You know, there's also some effect on dopamine.
Oh,
'cause
dopamine
we think
again.
about coffee, we think about, that alertness and that stimulant, and we think about epi and norepi, but what about dopamine? And I think in my mind, okay, well, we know dopamine is the reward system, right? So I would think somehow it would trigger the reward system if you loved coffee.
I would think so.
Right. And I think important to note is that there's some conflicting literature about whether or not coffee actually increases dopamine levels, but what is known is that caffeine can actually attenuate some neurologic diseases because it modulates the pathway of dopamine and it can protect against neuronal loss and it decreases the reabsorption of dopamine. So although it does have a lot of really seemingly beneficial effects on the dopaminergic system, it may not directly increase levels.
Interesting. And so I don't know. It's sort of give and take in a way, right?
Yeah.
Because you don't want to be running around with high levels of catecholamines all day long, because that can be problematic. That can be problematic for blood pressure. That can be problematic.
rate, yeah.
You know, there's some evidence out there that increased oxidative stress and high levels of catecholamine might be problematic, and but maybe at a certain level, it's somewhat neuroprotective too.
Interesting, right?
Very interesting.
Keep drinking your coffee.
Next time on the Lab Report, Dr. Jade Tita.
Yeah, naturopath, philosopher, athlete,
And a next level
author.
human.
No kidding.
I want to be a next level human.
You've been listening to the Lab Report. If you like what you hear, please subscribe to our podcast, rate us, and leave us a review. To learn more about Genova Diagnostics, visit our website at gdx.net. There you'll find information on specific testing, educational resources, and how to connect with our show. Call us at 1-800-522-4762 or email us at podcast@gdx.net. Yeah, so Easter's coming up.
Yeah.
What are your thoughts on those marshmallow peeps?
Peeps are another very polarizing candy.
Right.
They really are.
Gross.
Interesting story about Peeps. When I was in high school, I had a cat that was obsessed with Peeps.
Why would you give your cat peeps?
No, we didn't give them to her. I had to hide them when my mom would purchase them for Easter.
Oh my gosh.
And she would get into wherever I was hiding them, pull them out, rip the plastic open, and then eat the Peeps.
Did she think it was a real bird? You think that's what started it?
Yeah, I'm sure it was the accurate portrayal of wildlife that was confusing her.
Well, she was looking for the dopamine hit.
That must be it.